Swayam Prabha. Digital India. Educated India.
Hi, welcome back to Mechanics and Control of Robotic Manipulator. I am really thinking that you might have enjoyed the last lecture where it was showing something like very close to the real system, where you would have seen some kind of animated where the manipulator is moving. Although I made it restricted to only 2-hour serial manipulator, which is easy to show in you can say on a screen. That's why we have made it. However, it is not restricted only with the 2-hour serial or planar manipulator. It can be extended to even spatial. So, you can actually like do it that extension by your own. This particular lecture we are trying to show the workspace computation, how to make the workspace in MATLAB. So, why I have taken MATLAB? Because you can actually like generate a point, and the point you can make it as a cloud in a 2D plot or 3D plot. So, which will give the workspace environment. Then we can actually like see how the you can say end effector trajectory is going one to another. So, in order to get that idea, so we will actually like take this particular lecture. So, this lecture is going to talk about workspace computation, then the trajectory generated using task space scheme for same 2-hour serial manipulator including workspace. Then we can see like the trajectory generated using joint space scheme. Then we will actually like compare one to another how it is actually like happening. So, we will take a same case and compare it how it is actually like happening one to another. If that is the case, so we will move to the generalized 2-hour serial manipulator situation, where the initial position of the end effector and you can say final position of the end effector is given. In the other way, if you have inverse kinematic solution, so you know initial joint positions and final joint positions are known, provided L1 and L2 are known. So, in that case what one can see, first we will try to see, so what is the workspace. So, for that the theta 1 minimum to maximum you should know the joint limit. Similarly, the theta 2 minimum and maximum you should know the joint limits of the theta 1 and theta 2. So, once you know, we can actually like a plot based on the forward kinematics and we can actually like generate the workspace. So, provided you should know the forward kinematic solution. Since it is a 2-hour serial manipulator, the forward kinematic solution is straightforward. The x can be written as L1 cos theta 1 plus L2 cos theta 2, or you can say cos theta 1 plus theta 2. So, the y is actually like L1 sin theta 1 plus L2 sin theta 1 plus theta 2, right. So, this is we know. So, that is what we are trying to do. So, for that we are actually like taking it you can say the synchronous trajectory all the time. So, it need not to be explicitly given. So, anyhow that is actually like given here. So, now coming to the general case. So, here the theta 1 minimum and maximum. So, theta 2 minimum and maximum is given. So, in the sense the theta 1 you can say simulation, which is actually like I want to show where is the workspace. So, which actually like start from theta 1 minimum to maximum with the interval of 2 degree, because I just want to show only 2 degree interval of the points, it need not to be. Okay. Further, you please remember here I have written as in degrees. So, theta 1 and theta 2 all in degrees. So, whenever you write the equations, so you make sure that the units are matching. So, in that sense, so you can see the workspace I am trying to compute based on the forward kinematic solution. But what I am trying to do, so I am trying to generate the x and y for the given range. What the given range? The theta 1 vary from 0 to, or you can say minimum to maximum, theta 2 also vary from minimum to maximum. So, that minimum to maximum I have already defined theta 1 s, theta 2 s. So, I am trying to run the loop where the theta 1 is actually like running the first loop from minimum to maximum, the second loop theta 2 which is running minimum to maximum. In the sense first I will keep the theta 1, okay. So, you can actually like look at it here. So, the theta 1 is actually like coming here and the second is actually like rotating from minimum to maximum. Once done, then you move another and again rotate from minimum to maximum. Like that you can actually like do it in sequence. So, once this is done, so what you want to actually like plot Okay. So, for plotting we will actually like come back in the later, but right now I am trying to generate the trajectory. Okay. So, for generating trajectory what I know, so I know already the trajectory points which are actually like given to us. So, I am taking the same, but here L1 and L2 I have taken slightly different value. So, you can see it is 0.5 and 0.4. So, I did not take it as equal, so that I can see the workspace even if it rotates 0 to 360 it would be donut. So, the donut meaning you can say internal diameter is actually like 0.1 meter and the external diameter is 0.9 meter. Okay. So, I just want to show, but here it is actually like not going to be a donut, it would be a small patch. So, we can see that. So, before going to see that we can actually like take the trajectory variable. So, we will just take the trajectory generated in the task space. So, we will take the A as the same and Bx and By is given and Ax and Ay can be calculated. So, here we are doing it actually like independent trajectory generation. So, in that sense the trajectory is generated x of I and y of I like this, and the inverse kinematic model we have taken. So, then we will go to the workspace. So, here you can see the workspace I have plotted as a simple points across. I hold on, so that when I plot this all actually like plotted in that particular point. Okay. So, then I am actually like ending the manipulator motion animation. So, I have brought this, you can say 0 x1 x2 0 y1 y2, and that I make it as a line, so that it would look like animation. So, here actually like it is 10 millisecond as the delay, and again the same thing. So, starting and ending point we plotted, and the final trajectory also like we can actually like generate it. Okay. So, just to show that, so we will actually first finish the entire thing, then we will go to the MATLAB. So, the second case, so we are actually like trying to save this data. The second case is we are actually taking the inverse kinematics. So, then inverse differential kinematics where the theta 0 dot and theta final dot of individual cases are found. So, once these found we can generate the trajectory based on so and so thing. Okay. So, once these all found, so you can see like here. So, once those things are found, so we can actually like calculate these all. So, once these all calculated, so we can actually like calculate the forward kinematic model just for comparison. So, then we can again plot the workspace and plot the individual animation we can try to show. Finally, we will end with a comparative plot where you can say both trajectory how it look like, one is joint space, the other one is task space, how it look like, that we are trying to compare. So, for that we are actually like trying to plot individual cases. So, and then we are ending it. So, for getting more clarity, I already said it is a short video. So, for getting more clarity we will go to MATLAB, if anything we will explain then and there. So, you can see like here this is the starting point. So, we are actually like as general we are clearing the, you can say workspace, closing all the figure windows and clearing the command history, and the geometric parameter here link 1 is the length of 0.5 meter and link 2 is 0.4 meter, and the joint limits 0 to 2 and 210 degrees, and this is the simulation, and I am computing the MATLAB using for MATLAB for finding the workspace. The workspace I have computed, then the trajectory point details are given. So, I have actually like calculated all those things. So, then I actually like calculated, so you can see this, and again I have actually like calculated the what you call the B TH and this one. Then I calculated the individual joint trajectory coefficients, and the joint space trajectory I have generated, it is synchronous, and the other one is actually like independent, this is synchronous, and then I have tried to plot it. First I will run this, then we will go back wherever there is a clarification required. So, first I run this. So, you can see like this is the workspace, and based on the given condition you can see like the task space trajectory and joint space trajectory is giving some kind of peculiarness. Okay. So, that is what we are actually like trying to see. So, you can actually like look at it this. So, first I will try to show this is the joint space trajectory, okay. This is the task space trajectory. So, task space trajectory is actually like derived based on this. The initial velocity and final velocity is actually like making it little unrealizable. So I'll just make it actually like both are 0, and in order to make it standby, just to give an idea, so I am making it actually like 100 millisecond for the step for one image to another image. So now I am actually like trying to show here. So you can see this is the workspace, the patch part which is the workspace. So the first joint is actually like rotate 0 to 210 degree, second joint also rotate maximum 210 degree starting from 0. So if I plot, then this is the workspace will come. Within the workspace, this is the initial point and this is the final point. So now it is actually like from non-zero initial velocity to you can see finite velocity. So you can actually like see how it is actually like so complex, because we have taken the inverse Jacobian, which is actually like one such complex. So that is what it is actually like trying to do it based on so and so case. So here there is a peculiar thing we need to actually like see it. So I'll actually like try to show. So what happened here? So here we are actually like trying to calculate so and so this x1 dot and x2 dot. So since we are actually like clearing it there, so we are actually like clearing everything, right? Clear x, y. So this initial conditions which we have actually like calculated, you can see like these are still exist. So I make it initial and final velocity of both x and y are 0, and I just tried to show with a very simple 5 second. So I just want to show it here. So now I just, you can actually like see it. So it takes this point to this point, it is taking 5 seconds and it is running. So this make it, if initial and final velocities are 0, so you are actually like getting much smoother profile, right? So now we can actually like realistic. So for example, I am taking one point here, okay. So another point is somewhere here, okay. So what will happen in the task space trajectory, it will come here. So this point I am taking it actually like a 0.15 in x and probably 0 in y. I just take it. So I will take the initial point is actually like the same. So the final point is actually like 0.2, okay, this is 0, okay. I'll just try to see the plot, okay. So here I will be taking the initial point is something around, probably I'll take it here. So which is actually like 0.75 and 0.45, I just randomly take 0.75 and 0.45 just to show that. So the workspace, since we have not restricted the joint here, so the workspace will show, but the manipulator will show the animation says that it is actually like going out of the workspace, okay. So you can see like, it is actually like going to go outside the workspace in the task space trajectory. This is what we have seen, one of the concern which we were discussing in one of the lecture. So you can actually like see it here. So this is one of the solution we have taken, that's why it is actually like coming this way. So now the solution I am taking it, the other solution, we can see that other solution. So what is the other solution? So I am taking it, this is S2 is actually like minus sign, okay. So in that case, so you can actually like find, so this would be still outside workspace, okay. At least one solution is actually like possible, okay. This is also like going out. So probably I have taken some point from here to here, that would be clearly visible because both are outside the workspace, even the input is outside the workspace in this case. So that's why it is actually like not doing it. So I'll take it back. Okay. So I'll just run this and we'll actually like modify that. So I'll take one point here and one point here, then that would be within the workspace of both, we can see at least. So probably I take 0.75 and 0.45, and here somewhere around 0.25 or something. Okay, so I'll just see that. So in fact I would have taken a grid as the point. So this is the point 0.15 and 35 I take. So this is 0.15 and so 35, and the other point I am trying to take the input point somewhere here. So 0.8 and 0.37. Okay, so 0.37 and 0.8. I'm just taking a random point. So I'm just trying to demonstrate. So you can actually like see it. So it is actually like going to make it outside, right? But provided the joint space scheme is still following that profile. This is what we have seen as one simple case. So even I will take the other one. So the task space trajectory itself. So I'll take it here. So just mirror image I will take. So this I will take it 0. So just to show that where it failed. So it mirror image in the sense it is -1. You can actually like feel it in a single simulation itself. You can actually like feel it how this is going to be very tough. You can see it is going to fall in a near single, in the sense it is going to fall on a singular point, right? And you can see that it is giving the other solution, right? The task space which is giving the other solution, right? So you can actually like follow it. So this is what I was saying, if the solution of the same point which is having multiple solution, the scheme can actually like go it in a end of this. So why it is actually like just a mirror image of this. So that's why it is actually like giving the other solution. So now the same situation, if you do it in a joint space, we'll try to see whether that is actually like matching at least or not. Okay, so with that I'll actually like end it. Okay, so this one and this one, and we are trying to see. Okay, this is -1 I have to take, right? So this is -1. So I'll try to see whether that consideration of near singular and other thing is actually like restricted. You can see it is overcome, right? So this way, as long the workspace is available, even that solution is actually like exists. So that is what we wanted to see. So you can see like this point to this point in the task space, it is actually like going with what you call overlap with a singular point, but the other case it is actually like not happening it, right? So these all we wanted to check. So the same thing we can even do for a fifth order. Okay, so the fifth order actually like you can see only one change will come, the A matrix and the coefficients would get changed. So because of that, this you can say task space trajectory or joint space trajectory, so that you can say values will get changed, remaining all are same. So for example, I run, so the same thing we can actually like realize it, and it is actually like going to happen. So now I hope you are actually like clear to this, what you call how to find the workspace and how to actually like get the task space trajectory and joint space trajectory, and one, if it is failing, can we use the second one, or which is actually like beneficial and what instant it is beneficial, all those things you can actually like look at it. However, the task space trajectory is always better. However, like you can avoid certain constrained points, because that will give more realistic, because that is going to give in real time. Sometimes workspace means we always see only in the task space, but the workspace even we can realize it in the joint space. So here the workspace is actually like minimum to maximum of each joints. So here only 2 joints, it is in a plane. If it is a 3 joint, it would come as a volume. So similarly, if it is XYZ, that would come in a volume. So even we include orientation, that would come in the higher order dimensional, which is not directly visible to us. Okay. So with that, I am actually like closing this particular lecture. I hope this is actually like giving some clarity on so what is trajectory and how to generate a trajectory, how we can imply or how we can employ these schemes in the you can say serial manipulator and serial manipulator, what is the difference between join space and task space, these all you have realized it. So with that I am actually like ending this particular lecture, and the next lecture would be talking about control. We will initially start with open loop, then we will go to feedback which we call closed loop, then we will go the nonlinear scheme, then we can actually like close the subject with the advanced topic. With that, see you then. Thank you. Bye. Take care.